is on. Yeah. Okay. So who's going to indicate to me when I actually start? Good morning, everyone. The Jamaica National Heritage Trust is for this year celebrating its 65th year in existence. As in Jamaica, we will say from the mere fact that you've survived to celebrate 65, then it means that you filled up your 65 years and you're going over into your 66th year. So for this year, we started from December identifying the things that we've done. Now we know 65 is a very significant year. For human beings, it's a time when we think of retirement. These days, we classify retirement as an opportunity to do other things, to change of our activities. For the Jamaica National Heritage Trust, we will be looking at what we have achieved over the 65 years. We will also be looking at what we can do for, I dare say, the other 65 years. Now, the functions of the Jamaica National Heritage Trust are 4, as outlined in our Jamaica National Heritage Trust Act. The 2 that we will be focusing on this morning will be primarily the promotion and preservation of national monuments and anything designated as protected national heritage for the benefit of the island, and secondarily, to conduct research to support number 1. This morning, we have with us 2 professors who, as those of us who are viewing, be you online or in the room with us, will realize that these are 2 distinguished gentlemen who will be introduced in more detail in a little while. I take the opportunity to welcome you to this session. This, as you know, will be one of many that we will be using to highlight our 65th year of existence as the Jamaica National Heritage Trust and previously as the National Trust Commission. Please welcome and please open your minds, be stimulated by the presentations. We'll be having Q&A at the end, so those of you who are on YouTube or on the Facebook, please jump over to the YouTube channel and we are asking you for questions that you can put in the chat, which we will be entertaining at the end. So again, welcome, and please open your minds to be inspired by these 2 gentlemen. We are going to be having first Mrs. Howard Brown, our curator, who will be introducing Prof. Siegel, after which Miss Felicia Dawson will introduce Prof. Mitchell. Thanks very much.
Good morning, everyone. Welcome to the Jamaica National Heritage Trust, those on YouTube and those on Facebook. I'm here to introduce Professor Siegel. Peter Siegel is a professor of anthropology at the Montclair State University in New Jersey. He's a New World archaeologist with research interests in historical, ecology, ethnoarchaeology, heritage management and preservation, spatial analysis, cosmological and political organization. We didn't know an archaeologist did all of this, right? We thought they all did dig everywhere they went. But Professor Siegel will show us that an archaeologist is more than a person who digs the ground, but a person who does research. He has conducted projects through Eastern North America, much of the West Indies, Lower South America, and Eastern Bolivia. And more recently, he is in Jamaica on a Fulbright Fellowship. Information on his findings to date will be included in his presentation. And believe it or not, the archaeologists here at the Jamaica National Heritage Trust have really learned a lot from Professor Siegel. We have been seeing the artifacts in a different way. Not only what persons have left behind, but the history behind everything that they have used and what they use to make it with and how it impacts all of us. So I'd like to welcome Professor Siegel.
Good morning, everyone. It is also with great pleasure that I'm here to introduce to you one of our guest speakers for this presentation. Prof. Michel is a professor at the sedimentary geology at the University of the West Indies in Mona. He's also extensively studied the geology of Jamaica all over in the last 28 years and has mapped most of the islands and written numerous presentations and papers in geology. His interest lies in sedimentary geology, paleontology, and the tectonic history of Jamaica. He's actively involved in aspects of the economic geology, earthquakes, and the interpretation of what we do here at Jamaica National Heritage Trust, Archaeology. Please join me in welcoming Prof. Michel to the Jamaica National Heritage Trust.
Well, thank you, everybody, and thanks for this very nice introduction, Ms. Thompson and Mrs. Howard Brown. And so you see on the slide there the title of our presentation, Source to Sink, and as we progress through the lecture, you'll understand especially what sink means. I'll let Dr. Simon detail those. But I first would like to introduce the overall team that's been involved in this project, this research for the last couple of years. And so I don't need to read off all those institutions and departments, but it's been quite a journey of interdisciplinary collaboration, which has been very gratifying. So before I get into the details of White Marl, I just want to give a bit of a background. There was a similar kind of study done a few years ago, focusing on pottery from islands in the Greater Antilles. And Dr. William Keegan and his students did a pretty nice study tracing some of the potential trade routes in late prehistoric Caribbean, dating to more or less 1300, 1500 AD. In the lower left slide, you see a couple of images from the Jamaican National Gallery, wooden artifacts, quite amazing artifacts that show the kinds of sort of expressions of identity and sort of cosmological, sort of the thinking of what are commonly known as the Taino Indians. Dr. Mitchell is going to go into more detail about the geological context of this study, but this is a preview. And these are maps that were made by Dr. Mitchell for Jamaica. And so the red box that you see on the map of the island is the focus of our investigation of the White Marl archaeological site. And some of the questions that we're asking, you see in the bulleted items there. What's the extent to which White Marl ceramics were produced locally and versus traded within and across islands? It's a big question, and one that Keegan and his people were attempting to address as well. And then intimately related to that first question is, what are the source materials of the pottery? That's a major question. Where did they get their clays, the materials that go into the making of these pots? And on the right, you see a few examples of some pottery. White Marl was occupied from about 900 AD to 1600 AD, and this is based on radiocarbon dates. This is not White Marl. This is a village, an Amerindian village in Guyana, South America. Reason I'm showing this is to, in a sense, put the flesh on the bones of pottery production that we can try to get from currently living Amerindians and how they make their pots, and then we can gain insights into how it was done. So again, for those of you who are not really well versed in ceramic age archaeology, the people of White Marl, their ancestors originally came out of the Amazon, more or less about 500-600 BC. This is a picture of women making pots in the village of Shefarimo, and here you see clay collection from the river, an important aspect of collecting the raw material, and then the production of pottery. And so the pottery here is based on coil technology. You make these ropes of clay, and you circle them around a flat base, and then you gradually build up the walls of the vessels, shape them. Often use things like bivalves, shells to smooth out the coil ridges. In the lower left, you see a pot smoking, to harden it, and then finally you torch it, you fire it. And so in the absence of electricity and electric kilns, they build like these teepees of wood and put a pot right in there and fire it. All right, so getting into the White Marl study, when we first started this project 2 years ago, I spent a great amount of time in Mrs. Howard Brown's lab of the fines unit, looking through hundreds. The fines unit people were really very collaborative, brought up boxes and boxes of White Marl pottery, laid them out, and I would go through. And we wanted to shoot for a sample of 75. Here you see a couple of UE students who were taking a course in lab methods, so they came along to learn how to do this. And this is showing a bag of 75 pieces of pottery that we were sampled for petrographic analysis, which Simon will get into more later. And now I am turning it over to Dr. Simon.
All right, so good morning, everybody. So what we have done is to try and understand how we can relate the pottery back to where the pottery may have come from. So that's the real sort of key to working this out. And to do this, what we are using is the elemental compositions of the pottery. So the idea here is, okay, we've got these 75 pieces of pottery, which Peter very nicely talked about and selected for different reasons, because they were different types of pottery, different styles and things like that. But the important thing was that we wanted to cover a breadth of different types to see if they were made from different materials. So what we've actually done then is to say, okay, so they make pottery. Now, pottery is not as simple as you might think. Pottery is not just clay. It's mixed with other material, which is called temper, which for our purposes is sand. So what we end up with is we add in with a mixture of sand and clay, which then makes the pottery, but that makes tracing things using the elements a little bit more problematic. So what did we want to do? Well, we know that these things must have come from a clay source, and the obvious clay source is the Rio Cobre, and you can see the Rio Cobre winding there, and there's a big sort of yellow thing where White Marl is, and Peter went out and collected a series of sediment samples along the river, and one also further over in Rosetown, which is used currently for making pottery. So we really wanted to say, okay, does this relate to the pottery? Is this the source of the materials for the pottery? And how does it vary? How's it different? But also, where does this material come from? So we want to actually build that up into going to the geology of the island and what is important there. So you can see here that sampling went on, walking down a rather wet Rio Cobre and collecting clay samples and sand samples, although most of them really aren't sands, but that doesn't matter. But this gives us the raw material which we can compare against the clay sample or the pottery samples what we actually have. So, analysis. I'm not going to read through this for good reasons, but let us just look at it and think about it. We have information on the source areas where this material came from. And really, when you look at the clays, they can only come from the non-limestone rocks, which are exposed in what we call Cretaceous inliers. And there are 3 Cretaceous inliers, well, big ones anyway, which lie within the drainage basin of the Rio Cobre. Now, Alan Hastie, Dr. Alan Hastie, who's now in Edinburgh, and he's working with us on this, for his PhD, he collected all these rocks and he analysed them. So that gives us the actual geochemistry of the rocks in the Cretaceous inliers. Then we have the alluvial sediments and the pottery samples, which are analysed from this study in a series of different sets of analyses done in different places. And the ones I'm highlighting here are neutron activation analysis. And you can see a series of elements there. Some of them you won't understand, and I'm not even going to explain what they are. And then X-ray fluorescence analysis, which gives you some oxides and another set of elements. So we analysed all of these. And then I'm also going to throw in a little bit of X-ray diffraction analysis, which tells us some of the minerals, because that is actually quite interesting. And I'll explain why that is when we get to that point. So what do we do? Well, we also make thin sections. So at the Department of Geography and Geology at UE, we cut a series of thin sections, and then these were transported back with Peter, and we had a very able student who went through and worked out the percentage of different grains and the matrix in these samples using a technique called point counting, which is very tedious, to say the least. But what it does produce is it does produce here a series of numbers that tells you how much of different things are in the pottery, and also we lightly fired a little bit of the clays and the sands, so we also have the information for that. So we have that sort of information. And then we have the geology. Normally I'd get up and walk and say this, but since I'm sort of tethered here, that's not going to happen. So what you can see here, and I'm going to try and use the pointer, is this is the geology. Now I've nicely blanked out the white limestone to be white, and the blue line along the middle is the Rio Cobre, and you can see the Rio Cobre goes up, and it has 4 main tributaries. Let's see if we can. Okay, so here's the Rio Cobre coming up. White Marl is there. This is effectively the delta of the alluvial sediments, the sands and the clays, that has been built against the sea. This is Bogwalk Gorge, which many of you will know, for good or bad. And then up in here, you've got another alluvial basin up here, which is where Linstead and Bogwalk are, and you can also see the tributaries that come off. And the tributaries drain different inliers. So you've got one over here, which is the Cretaceous central inlier, and you can see only a little bit of it is drained by the Rio Cobre. Up here you've got the Bembo inlier, and about half the Bembo inlier is drained by the Rio Cobre. The other half is drained by rivers like the Rio Nuevo, which come in from the north coast, or drain towards the north coast. These are interesting because these are actually the oldest rocks in Jamaica, so that's actually interesting in that sense. And then you've got this larger inlier here, which is the above rocks inlier, and actually a lot of the Rio Cobre is sourced in the above rocks inlier. So it's those 3 inliers which actually provide the sediments which are used for making the pots. And these sediments are transported down the rivers and end up down here in the area which is most likely the area that was sampled by the Amerindians and which they used to make their pottery. You're not going to go a very long way to get material to make pottery It's not worth it. So, what do we want to do? Well, we've entitled this sort of source to sink. So our source is up here in the Cretaceous rocks. We get transportation down the rivers. It's deposited in a sedimentary sink, which is the delta system, and then that is sampled to produce a cultural sink, which is the pottery. And what we want to do is try and actually elucidate what is going on by using the geochemistry. So, first of all, let's have a look at those three inliers and look at the actual percentage of rocks that contribute to the Rio Cobre. And I think you can immediately see that the above rocks contributes basically 70%. The Benbow inlier, about 30%, and then a very small amount from the central inlier. Why is that important? Well, the actual rocks in those inliers are different, and they have different geochemistries. So we can use that to actually tag and see where the clays were coming from. Okay, so I'm going to use what we call multi-element plots. In effect, there's a load of different elements along the bottom here, which have different chemical characteristics and therefore react in different ways. I'm not going to explain that for obvious reasons, but what you end up getting is a series of what we call spider diagrams, which actually show the abundances or the concentrations of the different elements. This is in parts per million, and it's a logarithmic scale going up the side. And here you can see these two are the above rocks. These are a granitoid, a granodiorite, an intrusive rock, and then these are the lavas actually it's intruded into. And if you look at them, they're rather similar, the plots. Okay, the spiders are very similar to each other, if you like. And then you come to the eastern central inlier and the Benbow inlier, and these are the ones I picked out from Alan's data, which correlate to that. Now, if you look at it, you can see some differences. Look at these runs here. They're much flatter, lower concentrations than up in the above rocks. And these are similar. They're lower. They're notably lower. So you've actually got different geochemistries for these rocks, which means that we can look at the alluvial sediments and see, are they a mixture of these rocks, or do they actually type as one of them? So the alluvial sediments, well, they're characterized as sands. This is the collecting terms, and clays. But using the geochemistry, and I'll show you this, I can break them up into three groups. What we call sands, which most of them aren't sands. They're actually got a lot of clay in them, so we would call them wackies. And then we have two sets of clays, and the clays have some differences in some of the elements. Cerium and neodymium are things that you may not have ever heard of, and you don't need to worry about actually what they are. It's just that they're lower in one of them and they're higher in the other. So this is the point counting results. So the point counting results for some of these things indicates that some are nice clean clays. So if you look at the top here, don't get the pointer very often. So you look at these are good clays, okay, and you look at it and the actual matrix, in other words, is clay, is high. It's not far off 100%. So these are the sort of things they're using as clay sources. The rest of it is much higher in sand and wouldn't be very good for making a pot. And we'll see why that is significant later on when we actually look at some of the pottery results. I mentioned that we'd use a little bit of the XRD data. Now, this is the XRD data. It tells you the minerals that are present. And what I'm going to point out is that, yeah, there's quartz present, there's feldspar present. That's useful because that is going to be important later on. But there all of these other things, or most of these other things, are clay minerals. So these are clay minerals, these four here. And you notice the clay minerals of vermiculite and kaolinite, and there's no illite or smectite. Now, that doesn't mean anything to you, but one or two geologists in the room might realize that there is a significance, and the significance is that in a tropical environment, when you produce clays from igneous rocks, you have a lot of leaching, and you take away the alkali elements. And the most significant alkali element for our purposes is potassium. So that illite and smectite contain potassium, vermiculite and kaolinite do not contain potassium. So what we actually happen here is that the potassium is stripped out of the system when you make the clays, but it still sits in certain minerals such as feldspar. So what you're really saying here is, okay, that if you've got potassium, the potassium is not going to be in the clays because it's been stripped out of those during the weathering process. But if you've got still the feldspar there, that's a source of potassium. I dwelled on that because that becomes significant. Okay, so let's have a look at our clays. So these are our clays, and this is all the clay samples. And all of you can see, and this is the same plots we had before, that they only match the above rocks. They don't match the central inlier, and they do not match the Benbow inlier. Okay, so it's actually quite clear that these two, which are about 32% of the area drained by the Rio Cobre, do not add sediment or any significant amount of sediment to that lower part of the river. So we know that this material is all coming out of the above rocks inlier. That's good because it gives us a single source, so it helps us in terms of our analysis as we go forward. You might ask why that is, and that's very simple, is that the central inlier, the material from the central inlier flows into Lyth's Vale, and then it goes underground through a river system in a cave, and there's a big pool of material that is of alluvium that is formed in Lyth's Vale, and it all must be trapped there. And then the actual Benbow inlier flows down into tributaries which are dry most of the year. So you don't actually get much transport through that system, and anything there is probably just trapped within the northern part of the Lindstedt Basin. So you can explain why that's going on. And we now know that this is the situation, and we can type our clays, which must be coming out of the above rocks inlier. So we've gone from talking about the source area and showing that the source area is directly related to this sedimentary sink further down. Okay, lost something. Okay. Right, so what I also want to do is to show you some of the other things here, and this just compares the granodiorite and some of these clays and the sands, and I've selected certain elements in here because these ones become interesting when we get further on. So silica, or silicon, that's in many of the rocks, but it's particularly present in the quartz and in the feldspars. Aluminium, it's in a lot of rocks, but for our own purposes, it's in clays and it's in feldspars. And then we just talked about the potassium. The potassium gets stripped out of the clays, but it's in the feldspar. And then all these other things, this cobalt, this barium and rubidium, okay, those are substitutes for potassium, often in things. And so they are notably concentrated. And that is a very strange thing, which we picked up in an earlier study, which Shireen published with us. And the rubidium, very high rubidium, is actually a very strange characteristic of the pottery and the clays that are associated with the Rio Cobre. So it actually becomes a very good marker, together with the high potassium. Okay, so now let's come to the pottery. Now, the pottery doesn't match exactly the clay results. And I've split them into two types here, and I'm not going to go into too much detail on that, but you can see that some elements are similar. So these ones here are very similar. These ones are similar. But others are clearly depleted. Now, you might remember I mentioned that in making pottery, you add extra material, you add a temper to it. And so what we're seeing in this situation undoubtedly is that the temper does not contain the elements that are diluted. So these elements here are not in the temper, but these ones must be. Okay, otherwise they will be diluted as well. So what we're actually seeing here is we're seeing a characteristic. Now, if you accept that and you say, okay, something's gone, you can still see the patterns are actually very close to the patterns of the clays. So there definitely is a relationship between the pottery samples and the actual clays and in the lower part of the Rheacobrae. Look at some others. You can see there's a much better match there. Okay, so that one is using a temper, which is probably from the Rheacobrae. And then this is our group 3 pottery, which is 2 pieces. And it doesn't agree. It's not that far off on this, but if you look at the top here, you probably can't even see it, but these are a little bit lower, and down here these are a little bit lower. So there are some differences in that one. But the other differences on this one is the potassium and the rubidium. They're very low. They're not Rheacobrae-like. So let's look at some other elements. Okay, so what I've got here is I've got some of the actual elements. So let me just explain what this means. So I've got the clays and the sediments on this side. So here's the clays, the high neodymium, the low neodymium, and the sands. And then I've got the pottery types, the pottery type 1, pottery type 2, pottery type 3. I think immediately you can see that pottery type 3 in most of these is different. Much lower concentrations. Okay, it doesn't look like the rest. Okay, and then the other thing you can see is that, okay, the concentration here of potassium has gone up. Okay, not much difference there. Concentration here of barium has gone up, and the concentration of cesium has dropped, and that's about 40%. Okay, so you can see that you can start seeing that the pottery doesn't exactly follow the clays, and that some pieces of pottery clearly fall outside. Okay, so I've played a lot with the geochemical data, and we're still playing with it, but you can come up with little ways of classifying these things. So what we do is we use some different ratios. So there's a ratio down here, 100 times just to get the numbers meaning something that is useful, and logarithmic scales where appropriate. And you can start seeing in here, so you can see the actual clays are up here. They relate to these pots here probably, and then there's another set of clays here which relate to these pots down here. So what I think we're seeing here is we're seeing 2 different clay sources which were both in use probably at the same time, maybe by different potters. They had their favorite place to go and collect pots, or collect the clays to make the pots. So you've got these 2 major different sets of pots which are actually produced there. Then you can come down and we do another couple of diagrams. There's a weirdo over here. Okay, that one plots outside of everything else. So that's another strange one, and we don't have any clays that relate to that. So that's a bit odd, but it still has high potassium. It's somewhere in here. It's somewhere up in there. So it still has high potassium, so it still would suggest it's from the Rheacobrae. But then your type 3, you see, way down here. In fact, most pottery in Jamaica doesn't have this high rubidium, high potassium signature. So most pottery in Jamaica would plot somewhere lower down. So you can really quite easily distinguish the pottery that comes from the Rio Cobre. The type 3 pottery is also interesting for another reason. Okay, so you look at it here, this is a couple of things, calcium and strontium. And you see the two pots? One plot's down there, one plot's up there. One plot's down there, one plot's up there. Now you might be thinking, well, why? Well, when you actually look at a thin section of it, and we've highlighted it here, what's this? It's a bioclast or a fossil or a shell. And so what you've got in this situation is you've got marine material in this pot. So the temper used in this case was a marine sand which contained shells as well as things like quartz and feldspars and things like that. So in this situation we say, well, the difference in these pots is not that much. It's just a question of what they throw in. They're probably exactly the same source of clay, but that one was picked up, the sand was picked off a beach, this one was picked up from a river. WMS16, the outlier, it still has a characteristic of the Rio Cobre clay system. So it's still coming down the Rio Cobre clay system, but it has slightly differences in some of the trace elements. You can see that it's very flat in here. I think in here you can see it's very flat as you go across. And that's either a clay that we haven't sourced, or it's another river draining off the above rocks inlayer. And that's something that we aim to follow up with as we look at other sites. I just show it here that if you look on these diagrams, it's not much different. You know, it's sort of falling in with all the other pot types. So it's not really any different in those things, other than that strange difference in some of the actual trace elements. Okay, so that's the clays. Now what we want to try and do is to understand a little bit about the temper. Okay, so this is the point counting data, which is rather difficult to read and things, but we can summarize it, and I put it here, and this is the summary. The interesting thing, look at the mean, the matrix, the clay material. Look at the range, 60 to 63 basically, 61 to 63. It's remarkably narrow. Group 3, we only have one piece of pottery which we actually point counted. It's the same range. So there's really a very, very stable amount of sand to clay ratio in these pots. It's always in the ratio of 3 parts to clay to 2 parts to sand. And that must be a recipe for making pots. Okay, so you use a pure clay, and you take 3 parts of clay, and then you use a pure sand and use 2 parts of sand. And experimentation must say that makes good pots that don't blow up when you fire them. But the remarkable uniformity of all these measurements is really quite something, which does say that this is not by chance. This means something. That's what they look like. So that's one. So you can see the grains in there, and you can see the mud in the background, which now is not mud because it's been lightly fired. It's gone into some other forms of minerals which we haven't identified. So let's have a look and see what elements might be in that temper. So let's compare what is present in the actual clays and what is present in the pottery. And so the pluses here mean that it's much higher in the pottery, or in the temper, which was added to the pottery. Minuses mean it's less. So you can sort of get an idea of what was in the temper. Bear in mind we've got that 60-40%, and you can see that a lot of these, elements, 60, they're in 60%. So that's showing you the temper added. So the ones that didn't contain the temper, or sorry, the elements not in the temper basically show about 60%. And then the elements in the temper are elevated. And so you end up by saying, well, the temper contains these things, some of which you've probably never heard of and you might never hear of again, but that's life. It's interesting, if you look at them, the sodium, the potassium, the rubidium, the strontium, the barium, they're all in the feldspars. We know they're not in the clays. We know that the clay doesn't contain the potassium. So it's quite clear that the temper must have contained a rich feldspar source. It's got to be feldspar rich. And the silica, because you can, I don't have silica there. No, I do have silica there. See, silica's elevated as well. That's going to be quartz. So it's quite clear that the temper contains quartz and feldspar. So it's a pure sand from the above rocks, because that's what you'd find in it. But there is another little tree there, this is the zirconium, so there's a few heavy minerals in there as well. So I think we can actually say, well, we didn't actually manage to sample it, but we can identify what the sand would be, and the sand is consistent with it coming from the above rocks inlier as well. So I think we're now in a situation to sort of say, okay, we do understand now from the source to the sink of the actual pottery manufacture in this place. The igneous rocks were weathered as they came up. So as they were uplifted, they were weathered, and they were transformed into clays, but the alkalis, the sodium and the potassium, were stripped out, which is the normal explanation. I mean, that's how you make bauxite. You strip out all the alkalis, and in fact you strip out the silica as well. And if you do that enough, you end up with bauxite. So we know it happens here. The erosion of the inliers, the clays get washed into the rivers, and then bits that aren't so weathered, they get washed in as well and provide the sands. So you end up with sands and clays being transported along these river systems. But of course, clay is nice and runs easily in water and gets transported easily. Sand, you have to have a storm to transport it, and so they're deposited in separate beds. So when you get down into the delta area where the settlement is, the White Marl settlement, you've got individual beds which are going to be sands, you've got individual which are clays, and the clays are what you sample for your raw material for the clay part of the pots, and then you look for the pure sands for the temper in the pots. So we have this sort of pattern. This is where we started. We had this on the thing, and this sort of summarizes what's going on. So you've got the fresh rocks here. That's a nice fresh granodiorite. Gets uplifted, gets weathered, gets eroded from the mountains, goes down the river system and sorted out into beds, deposited in the delta system, and then the clay and the temper is sampled and used to manufacture the pottery. So what we can say here is that this first part of the conclusions, anyway, we can say that using the multi-element plots to begin with, we definitely can see that the alluvial sediments came from the inlier, one of the inliers. They came from the above rocks inlier. And then we can actually, basically using the same sort of plots, we can say that yes, the pottery shows the characteristics of these, and you can actually match it back to those, but with the assumption that it's been changed by the adding of temper. And we can split the clays into two types. I haven't really gone into it in great detail, but high ND and low ND clays. And we can trace those pottery back to those two types of clays. The high potassium and rubidium concentrations are quite significant. They really are unique for the pottery in this part of Jamaica, and they act as a very, very good marker for material that's come from this inlier. There might be a little bit that comes out some of the inliers further east, but they are also going to have different geochemical signatures. So looking at this in Jamaica is a very good idea because we've got a very varied geochemistry of these rocks across Jamaica. The point counting demonstrates that basically they're using 3 parts clay to 2 parts sand to make their pottery, and you can see that coming through into the concentrations of certain of the elements. We can go and say the temper clearly includes something that is very rich in feldspar and rich in quartz, and the geochemistry just tells us that, and so we actually can tell what the 2 main ingredients were with the pots. A single outlier is there, which has the same high potassium rubidium, but is different from the other clays and may have come from either a different clay we haven't identified, or maybe a different river system draining the above rocks. And then 2 samples don't belong. They have low potassium, low rubidium, and plot in a very, very different place. One of them has a sand temper which actually has elevated calcium, strontium. I didn't show you the diagram, but there's more sodium in there as well. And we all know that the sea is a bit salty. So you can explain that as marine sands being used as a temper source. We are speculating this is probably from the Rio Cobre, the Rio Minnow, but that is where we are going to next. Peter.
Reason I'm showing this slide, and I showed the same image back in September when I gave an earlier presentation here at JNHT. So when Simon was talking about the neutron activation analysis that gives you relative percentages of different elements in these samples, whether they're pottery or clay, this is just 4 out of like 31 of these plots. The reason I'm showing it is that the same 2 pieces of pottery, sample numbers 3 and 16, that Simon was talking about as sort of being unusual, shows up very dramatically in these kind of plots. So those you see in the 4, you see most of the pieces of pottery are clustered into where you see them with the oblong around them. And then, but 2 of them are always outliers. And they're the same 2 pieces of pottery that Simon talked about a few minutes ago. And so here's, so out of 31 total elements that we measured with neutron activation analysis, I think I have the wrong number up there, 68. It should be 16. 68 is correct? Okay. Yeah, okay, that's right. So 68 and 3, so for sample number 68, it was an outlier 31 out of 31 times, or 100%, you see on the right. Sample number 3 was had different concentrations of elements, 30 out of 31, or 97%. And then 3 others were lesser amounts of in terms of percentage. So I just did a little at the bottom where it says total elements analyzed 31, total number of sherds analyzed 75. So if you just do the simple, percentage ratio, we can extrapolate that we can. All right, remember, for those of you who've worked with white marl pottery, and you know how many boxes, you have boxes and boxes and boxes of pottery here at JNHT. They also have many boxes over at UE Archaeology Lab. There's a lot of pottery. I don't know how much it is. Maybe Mrs. Brown knows. I would say, what, 1 million pieces? I don't know. But that's just a sample of what was just, that's only what was excavated. White Marl site is enormous. So there's lots of pottery out there. These people were producing pottery on an industrial scale. So we only looked at 75 pieces. So if, say you just look at the two, 68 and 3, and unfortunately I forgot to bring my regular glasses, so I can't read the slide here. But if we just say, what does it say? 3 divide, so if we take the first 3 pieces, 68, 4%. So that's 4%. So if you take 4% of, I don't know, I'm going to make up a number, 5 million pieces of pottery at White Marl, whatever it is, 4% times 5 million will produce some number that's fairly significant. So what this is showing us, or suggesting to us, is that some of the pottery was coming in from elsewhere. Well, that may not sound so astounding, but one of the big issues in archaeology worldwide these days, especially in, well, not prehistoric, in historical as well, the prehistoric and historical archaeology, are talking about trade and exchange networks, communities interacting with each other. Just like in the real world of today, you may have grown up in Kingston, but you may have family in, I don't know, Manchester, whatever. You interact, you travel, you get together, and sometimes you bring gifts, especially if somebody's getting married, you bring a gift. Well, the same sort of social processes were going on with humans ever since we've been human. And it's no different here at White Marl. And so the thing is, trying to establish these kind of networks realistically with some data, this is how you can potentially do it. Now, this is just the first start. We're just talking about White Marl site. So follow-up to White Marl, and many of you in this room now are intimately familiar with this because you've been gracious enough to take me out to various places of Jamaica to collect samples. We're collecting pottery from 16 other sites across Jamaica that are more or less about the same, occupied at the same time as White Marl, okay? About 12 to 1500 AD, more or less. What we're doing is going out to these known archaeological sites and looking for clay and sand samples in the locations of each of those sites. And then what the plan is to conduct the same analysis that you just heard Simon go into excruciating detail as we did with White Marl. And this, if you read up on the literature of Caribbean archaeology that's going on today, this, I can just tell you, this will be one of the most data-intense pottery studies across the West Indies. There have been quite a few good studies. In fact, I'm guilty of this myself. I did a study pretty much like this about, I don't know, some years ago now, from pottery from Puerto Rico, from a very large site about the same size as White Marl. And we did neutron activation analysis of about 50 or so pieces. What was really missing from that study is I did not go back to the location. I did not walk up the river. Can't remember the name of that river now. And collect clay samples and compare it. You need to have that as your point of comparison. And so it's only with these on-the-ground soil surveys, as I call them, for doing this, that we can then come up with realistic and accurate models to reconstruct trade and exchange patterns. And so I would like to just end this by acknowledging JNHT's great support in this project. It's been quite amazing. These are just at the end of each field day, we take a crew shot. So this is 2 of the crew shots. Mr. Walters was on there on the right. He was on the very first day we went out. That was a horrible hike, going up to trying to find Rodney's house with all this cactus, and we never actually made it there. So these are a number of the members of the team that have been working on the white marl study. They come from the various institutions that I showed at the beginning. Well, you see them in the captions down there. Between collaborators and acknowledgements, you see the names of those various institutions that have input into this study. So on behalf of Dr. Simon and myself, thank you.
Okay, thank you very much for your attention. While I was monitoring the YouTube chat, I did not see any questions. So I'd like to ask now, do we have any questions in the room? I usually say when the presentation does not stimulate questions, it's either that we understand nothing or we understand absolutely everything. Since we're on YouTube, I'm going to assume that we understand everything. Are there any questions again? All right. The beautiful thing about, okay, sorry. There's a question there. Can you just come up, please? Or, okay, so you're going to say your question. The relevant prof will interpret and respond to it. Thanks.
Okay, well, the titanium, what you got to realize is that what we're doing is we have to look at the processes that go on that form the original rocks. This is where Alan is working on these sorts of things, and basically what happens is that different minerals crystallize from igneous rock magmas at different times, and they take out certain elements. Equally, when the igneous rocks, the magmas, are being produced to begin with, down in the volcano, you get partial melting, and different elements are put in different concentrations into that, depending on the stability of the actual minerals they are actually in. So you've got these processes of actually the melting, partial melting. It's not all the rocks that melt. So when you're looking at a subduction zone where you've got a slab going down, like in the Lesser Antilles, below the volcanoes there, as that material goes down, some of it melts. And because not all of it melts, only certain elements go into the melt. So it gets concentrated on certain ones. And then when it starts crystallizing again, when it comes to the surface, and you get crystallization in the magma chamber, and things settle out of it, and therefore what's erupted, it isn't exactly the same. So you're really talking about various types of fractionation, and titanium is one of the things that actually ends up like that. And in fact, when you actually look at it, a titanium spike like that indicates these rocks were once part of a subduction zone and formed in an island arc. Well, that's different from the archaeology, but that's the understanding of it. And the reason why the original rocks, when we actually looked at the spire diagrams there, the reason they are different is because the material going down that subduction zone changes over time, and different bits melting give you the different concentrations of those elements. So it's all about that. Now, if we went over to far eastern Jamaica, which is where we're looking at Duckenfield, we've got a site over in Duckenfield, that comes from a completely different set of igneous rocks. And if you look at those, they're completely flat. The spider diagrams are flat. Now, what we're anticipating, correctly or incorrectly, I don't know, is that we might expect to see pottery there that has the same flat signature. And that would tell us that's local pottery there. And if we see something with a signature of white marl, we say, somebody brought me a pot from white marl all those years ago. So one of the reasons why it is so useful to do this in somewhere like Jamaica is that the igneous geochemistry is really quite different across the island. And I mean, in middle bit between us and Far East and St. Thomas, there's metamorphic rocks in there, which we probably see in the tempers. So we have a very, very good, what I say, base level geology, which will enable us to address the question of where has the pottery traveled from. If you went up onto the west coast of the USA, you're going to find the same sort of processes going on all the way along. You're not going to be very easy to actually distinguish pottery in those areas by this sort of mechanism. But in somewhere like Jamaica, which has had a rather traumatic geological history, to say at least, it helps us when we're actually asking these sorts of questions. And that's why I think it's great. And that's why I think it's so important that different people from different backgrounds are working together to basically come up with a nice solution to these things.
When I said before that, you know, data intense. When I said before about this being a very data intense project, it relates exactly to what Simon was just saying. So, like in St. Thomas, Spanish wood site, which according to Simon and his geochemistry, is going to be very different. And so if we're doing this in 16 places around the island, we have the potential to start coming up with a fairly fine-grained sort of social model based on geochemistry and all that, about where things are moving around the island. We can be able to back it up with some pretty good data. And then we can start talking about other more, what I consider as an anthropologist, more interesting things like what's the what's the human behavior behind all this business, you know? So, right. And I just when Simon was talking about temper, do you all know what temper what it is? Okay. When you make a pot, you just can't make a pot from clay that you collect. You have to mix it, and that's what Simon was talking about. This recipe of what three, and so I should have mentioned when I was showing those pictures of the YY Indians in South America making pots, you saw in and amongst all that activity, they had these bowls of material, bowls of sand, and they, oh right, yeah, there, see the bowl there, and so they're mixing in. They were sort of like making bread, you know. They were mixing in and then kneading it, you know, to make the clay suitable for then fashioning it into one of these ceramic vessels. We don't know. We would love to know if they use 3D. Well, back then I always think about, this is when I was young and stupid, and I was making good observations, taking photos, but what I should have been doing was then quantifying, you know, looking at, well, how much of that sand are they putting in that pot, you know, like get out and make them put it into a measuring cup first before they, you know, and yeah, it's always an if. Yeah, you know, but I hadn't thought of that until, you know, more recently.
Okay, I still did not see any question in the chat. Have we exhausted our questions and our discourses in-house? Okay, yes, go ahead. We have 2. People are being stimulated. Excellent.
Yeah, that's an excellent question. And the earlier slide I showed from Bill Keegan, that's what they're attempting that one, where you see those arrows going from Hispaniola up into the Bahamas. They believe that pottery was moving from the big island of Haiti and Dominican Republic up into the Bahamas archipelago, and I think from the work that we're doing over there in Jamaica is going to give a very good basis to start doing this realistically and accurately across islands potentially, to answer your question. And we know, I should have put in a map of the Caribbean showing the migrations of people. I have another map like that. Yeah, but people were interacting with each other all through prehistory here. They were very good at making canoes. The ocean was not a barrier. The sea was not a barrier. It was more like a highway that they used to get around. And we can see that in the styles of pottery. They're somewhat different, like the white marl style, which is called the Mayak and Osteonoid subseries from Irving Rouse. I spent many years working in Puerto Rico, and so from my Puerto Rico background, I see many similarities. And so I think there was a larger sort of worldview that these people related to, but they expressed their identity somewhat differently locally, Like each township here in Jamaica, or I know where I live in New Jersey, has its own township flag. So I live in West Orange. We have a flag of West Orange that's different than the next town of Newark, New Jersey. And then the state of New Jersey has its own flag, which is different than Pennsylvania. And then the United States has its own flag, which is different than Mexico. Your ways of expressing identity are sort of show up in different ways, and I think the same process applies in the production of this pottery and the styles of it.
I was going to also add for this study here. One of the things about this is that you've got to realize that a lot of the Bahamas are just carbonates. So there is no source of clay on them for making pottery. So in those situations where you actually find clay from those places, it's got to have come from somewhere else. People want pots for obvious reasons. So in that situation, you've got to bring those pots in. They're probably going to be more valuable than the pots where they were sourced, simply because they are a commodity that you have to bring in, and that's going to be expensive. So here they're sort of indicating they're all coming out of Hispaniola. Now, the point I will say about this is unless you look at the clays very carefully, you're going to have very similar clays that go through Hispaniola and up through Cuba. So those directions may be right, but they could also be coming out of Cuba. Or, as Peter sort of mentioned, from Puerto Rico as well. You're going to have very similar rocks all the way up through those. Okay, and in fact, you get similar rocks in Jamaica as well. And then if you look at the eastern Jamaica, I was talking about having very distinctive character. If you go into the southern peninsula of Haiti, they have the same rocks there. So when you're talking about if we find pottery with the same characteristics as some of the things in Jamaica, in Trinidad, for instance, does it mean it's come from Jamaica? Not necessarily. It means it's come from somewhere that has a similar geology and creates a similar geochemical signature. That won't be Trinidad, because Trinidad has a different signature, because Trinidad is basically part of South America, not part of the Caribbean arc. So it's going to have a different characteristic. But then you can look at other things, and what you use in other things, there are certain materials, and obviously the one that comes to mind most obviously is jade, which only occur in a very small few places within the Caribbean. And because people value those, and they're much higher value items, those ones you find distributed across different bits of the Caribbean. And you can actually trace those back. So as well as the pottery, and the pottery, because we have so much of it, we can do it with, we can work out one story, but then for higher price items, you might well be able to work out networks there, but that may be a different sort of network, because that might be a bartering system and not something else, that the reason that these things are passed on. So putting all of this together, putting all these things together allows Peter to sort of answer some of his questions, I hope. That's the idea, anyway.
So far, what have been some of the major challenges or limitations to this project, and how have you overcome?
Okay, well, there are a number of challenges. Let's just go through some of them. It takes a very long time to... We mentioned the point counting. It takes an extremely long time to point count. So we have 75. I think we got 20 done. 22? 22 or 23 have been point counted to this point. Okay? Yeah. So it takes some time. Somebody needs to know what they're doing to actually count them. You'll notice some of the pottery types didn't have any point counts done, and we're trying to get those done at the present point in time. So that's very time consuming. Different techniques we've used to identify different groups of elements. Now, so some of this is done in Missouri, some of this is done in Germany. The Germany ones only ran 20 of the pots, so we only have some elements for some of the elements we only have for a very small number of pots. And that means that when you come about trying to do principal component analysis, multivariate analysis, you can't do it with it, because you've got to strip those out, because you're not going to be able to have enough. Well, they were not going to count. They will get removed in the processing. These sort of analyses aren't cheap. So we have to find people, we have to either find grants, or we have to find people who want to be involved in it and help with this because they think it's a good idea. So there's a financial constraint on things as well. We're using pottery in collections, and some of those collections are not very large. White Marl obviously has vast amounts, that's not a problem. But some other sites only have a few sherds. And that obviously, I mean, you see, out of 75, 2 came from somewhere else. So if you only got 20 in a collection, you're probably not going to get anything that's from anywhere else unless they're all from somewhere else. So again, we're limiting our sampling. We can't sample 1,000 pots from White Marl. It would be lovely to have the data, but there's no way we can do that. And again, we're teaming up with people here now. So with ISANS, we're teaming up to do some of the neutron activation and analyses here, so that they'd actually done in Jamaica. So there are lots of challenges. But yeah. Anything else you want to add, Peter? I mean, I think, yeah. The river systems change relatively frequently in Jamaica, and people don't really, I think, appreciate how rapidly some of them change. We often have a way of looking at it and picking up the map, whatever they happen to be, and just looking at it and saying, oh, that's where the rivers go. And in fact, the boundaries go along some of the rivers for parishes and things like this. The other day I was playing with a rear minnow and looking at the the detailed map is the 1 to 12,500, which is based on the 1969 aerial photographs. If you actually look at the modern river system, and you can pull it up on Google, well, Google Pro is, I tend to use, you get better results from Google Pro, which is now free, so that's not a problem. You'll see the river has absolutely no resemblance down in the Veer Plains to what's on that 1969 map. Absolutely no resemblance. You can still pick where it is, or where it was, because you can see lines of trees, which used to be on the bank of the river, and now it's all just basically filled in. So these river systems are actually quite dynamic when you're actually looking, you know, and that's what, 69 to now? You know, that's what, 50 years or so, 60 years, 70 years. It's not that much time, and if you actually project that back to the time when these sites were occupied, they're going to be very different. So the clays we see today on the riverbank aren't probably exactly the same clays that they were sampling anyway. So these will have changed. I mean, our assumption is that they're relatively similar. I mean, I had a good idea that this had happened in the Rio Meno when many years ago, I think 1998, I think it was, or something like that, when we had a project looking at the Rio Meno in terms of a resource assessment for the sands. And we walked along there and we found at the bottom, in the banks, embedded in it, a piece of metal. Modern-ish metal. And that immediately told me, well, these floodplains aren't very old. And you basically, I think people have a false sense of security that it's always going to be the same. I mean, I think when we get tropical systems come through, I think people realize that, yeah, these rivers do move. People lose houses and things like that. I mean, these things are not stable when the banks are soft. You know, yeah, if you can see that with one passage of one tropical storm, you start projecting hundreds of years. Yeah, you really are starting to say, well, these systems are going to be different, and they're going to change over time. So yeah, they're dynamic. They're dynamic, and there's no way you can stop them moving. I know people would like to secure their houses, but I'm afraid Mother Nature has a different idea about some of these things.
Okay, we have exhausted, we have eaten, we have masticated, we have enjoyed, and we have been stimulated from the presentation from Prof. Siegel and Prof. Mitchell. To those of you who in cyberspace who've been fairly quiet for the duration of the presentation, we want to thank you for having attended. The beautiful thing is that you can share this information with those with whom you come in contact. We can go back and look at it, because I'm sure we will all agree that these gentlemen gave us a loaded presentation, things that take quite a while. It's like the cow that brings up the food after it has eaten and decides to churn on it to crush it down. It's a similar thing. Yes, Mrs. Howard-Brown. It's a similar thing. Please forgive me, I'm a scientist. It's a similar thing with this, where repetition deepens emphasis. And therefore, that's a little bit better, right? And therefore, we're going to be going back. We're going to be watching this presentation. We're going to be sharing it with our colleagues and our friends. We're going to also be looking forward to other presentations based on what both gentlemen have said. More research will be going on, and therefore we will be looking at the education that will come out of this, because all of this research serves no purpose if we're not passing the information on to the public, if we're not sharing it to those, not those who are presently our contemporaries, but also those who will come for posterity in the future. And therefore, I want to thank all those who have been with us in this boardroom. We want to thank those on cyberspace who've been with us. We want to thank OCM Productions Limited, our technical team, for facilitating this. We know that behind the scenes is what's going to give us the posterity in this presentation. Thank you all for coming, and we will keep you, Jamaica National Heritage Trust will keep you posted on other activities, including the one that is presently going on, the dive that's presently going on in Port Royal in our sunken city. We'll keep you posted as to other activities that we will use as landmarks to celebrate our 65th year of existence. Thanks very much for coming, and there is refreshment on the outside. Thanks much again. Do have a good rest of the day.
Do check out our website at www.jnht.com, our Facebook page, and you can follow us on Twitter at JNHT Jamaica and on Instagram at JNHT1, or email jnhtpublicrelations@gmail.com, or call us at 876-922-128728. The Jamaica National Heritage Trust has the legal mandate to protect, promote, and preserve the nation's rich cultural material heritage. The agency legally declares or designates places and objects of historical value as national monuments or protected national heritage. It is our mission to inspire a sense of national pride through the protection, promotion, preservation, and development of our cultural heritage, utilizing a highly motivated and qualified team. Visit the Jamaica National Heritage Trust at 79 Duke Street, Kingston, Jamaica, West Indies, or at www.jnht.com, or call us at 876-922-128728. The Jamaica National Heritage Trust, enriching our heritage.